Hi guys, here we go. We should be on Unit 10, Day 1 notes, starting this chapter off with exponential growth. So today we're going to talk about exponential growth, kind of talk about exponential decay, but tomorrow we're going to focus a lot more on the decay part of this. So let's fill some of these pieces out. When we're talking about exponential growth, this means something is increasing. It's growing, it's getting bigger, it's rising, something like that. So it looks like, let's see here, it could look something like that. Okay. Decay, on the other hand, is going to be something that is decreasing or going down, getting smaller, something like that looks like that instead. Okay, let's look at some examples just right down below where we're going to focus just on growth, but some examples with the numbers so you can kind of get a hang of what like the formula and the traditional formula looks like. So it says example 1, using the given equation fill in the blanks, then give a sketch of the graph. So I'm going to focus on problem A on the left hand side first and kind of pick apart some of the pieces so you know where to label. This first one says to rewrite. When I'm going to rewrite this, I'm going to rewrite this as almost looking exactly as we have up top, but, and I left like a blank space in the parentheses here, but this piece in parentheses I have to adjust. So like the f of x is the same, the 4 is the same, the exponent there, all the same. The inside, I have to rewrite it with the 1 plus in there. I have to put a 1 because that's just in our standard form, and I'm going to put a plus sign because I know this is a growth. If I have a 1 plus in there and I want to get it to match 2.45, then I have to insert in a 1.45. Because I know when I add up this yellow piece in parentheses, I want to get back to the other yellow piece. Those should be equal. I didn't change it necessarily. I didn't change the number. I just kind of rewrote what it looked like. And that's what we're doing on the rewrite. Now, this next piece, the initial value. The initial value is going to be the number in the front. So my initial value is going to be 4. Or, if this helps you, you can write this as a coordinate 0, 4. And I'm going to talk about this again in a second. The next piece is growth or decay. Let's figure out, is it growing or is it decreasing? Well, an easy way to figure this out is you can look at the number in the very beginning, the 2.45, and you can compare it to the number 1. If that number is larger, which 2.45 is much bigger than 1, then we know that this means it is a growth problem. So that means I can go back down and circle growth. Again, the reason is 2.45 is bigger than 1. Then it says, well, if it's a growth problem, what is the growth factor? Now this is where it gets tricky. The growth factor is whatever you used in the rewrite. So I'm going to put a blue arrow right there. This is the 1.45. This is the number you used in the rewrite. Okay? Then it's saying, okay, it's a growth problem. Here's my growth factor. Well, how much did it increase by then? What was the percentage? So you're going to take that 1.45, and just like we practiced, we're going to kind of loop that, move that decimal over 2 times to turn it into a percentage. And when I turn that into percentage, I loop it over twice, I get 145% increase. The reason I know it's an increase is because it's a growth problem, so that would mean it's getting bigger, it's increasing. So it's a percent increase. If I went too fast, pause it, rewind it, maybe get some colors out so you can color code it so you know, okay, the initial value came from the number in the front. The growth factor is where my blue arrow is right here, all of those pieces. Now, using those pieces, I'm going to make my graph. My graph is not going to be exact, it's just kind of giving me a rough estimate. What I'm going to use to get my graph started is the initial value. The initial value is at 4. So that means I can go up, and I'm just going to kind of sketch those in. I can go up 4 spots. That's why I said it's the coordinate over 0, up 4. And since I know that this is a growth problem, I know that all of my growth graphs look something like that, going in that direction. So there is my very rough sketch. Okay, let's practice on a different problem, just scooting over a little bit to problem B. First thing, gives you the formula or the function, g of x is equal to 0.65 times 1.5 raised to the x. Okay, first thing is to rewrite. I keep everything pretty much exactly the same, except for the stuff inside parentheses. I'm going to leave that separate, or kind of leave it out. I want 1.5, but I know I'm going to have a 1 plus in there. I must have a 1 plus 0.5 if I want those pieces to match. Not like I'm changing it, I'm just kind of separating it out so that it would be the same thing. Okay, then from here, the initial value. The initial value is the number that I just highlighted, the 0.65, the number in the front. Or if you really like to write that as a coordinate, 0, 0.65. Now, growth or decay. This is where you look at the very beginning, the stuff in the very beginning in parentheses. That's 1.5. You compare it to the number 1. 1.5 is larger than 1, so that tells me that this is a growth problem. I can go back down there. Again, my reason is because 1.5 is greater than 1. The growth factor, and again, this is tricky. You have to look at where you rewrote it. So I just highlighted it yellow. The growth factor is 0.5 for this problem. So then if it says, well, what is the percentage? I'm going to take that 0.5. I'm going to loop my decimal over twice. I rewrite this as 50% increase. How I knew it was an increase is because I have a growth problem. That means it's getting bigger. It's growing. So if I use those pieces to make my sketch, I want to plot, I should make those a little bit bigger. I want to plot my initial value. My initial value is at 0.65. So that means I go up 0.65, which isn't that much, it's right about there. And since it's a growth problem, it looks something like that. Again, similar graphs, the initial value, where it's starting for both of these graphs, are different. If you're confused on any of those pieces or where they came from, pause, go back, rewatch it, see if you can figure them out or find them on your own. If you're ready, go ahead and flip it over. We have a couple more kind of word problem examples. We're going to be using the formula, which I'll give you in a second. Here's our scenario. There's a pond stocked with 200 fish, and the Department of Wildlife expects the population to increase, so grow, at a rate of 5% each year. How many fish will there be in the pond after? And then it's just asking you, well, write an exponential growth equation to model the situation. So it just wants you to know, like, if we wanted to know in 5 years how many fish, then we could plug in and get our answer. Or if we wanted to know, like, well, how many fish will there be in 50 years? We can plug in a 50, the number 50, and then get out our answer. So it's just kind of a general formula for us to get these possible outcomes. So before I pick through the numbers, I want to give you the equation. It is going to look like y equals a times 1 plus r raised to the t power. Okay, bunch of letters. Let me give you the pieces. The y is like your final answer, or like your solution. I'm going to write final. A is what we call our initial amount. How much you started with. R is your rate. And this one's really important. I'm going to put a star because you need to put this in decimal form. Then T up here on the outside, you probably guessed it. This one is for time. How long? Okay, those are the pieces. We got some numbers. We have a scenario. Let's plug into it. I'm going to back up a second and kind of go back through my pieces here. The first piece says the pond is stocked with 200 fish. That is our initial amount of fish. So that is our A, how many fish we started with. They expect the population to increase, so that would be a growth problem, increase at a rate of 5%. Well, I have to change this 5% to a decimal. So that means I'm going to go backwards now 2 loops, and I switch that into a decimal, which is 0.05. Then it wants you to know, or wants you to figure out, how many fish will there be in the pond after. That's kind of talking about time. The time, we don't know. That's what it wants us to model. So I'm going to put a little question mark there. So now I'm going to plug in. I have y equals, because that's my answer. The initial amount of fish is 200 fish. And then I have a 1 plus, because that's always in there. My rate, which we just figured out, is 0.05. And then raised to the t power. T is for time, right? And we don't know how much time. This would be our model. This models how much. So again, somebody could put in 5 years and for time, get an answer. Somebody could put in 100 years, get out their answer. You're just kind of setting up the general equation. Let's try it again. In 1998, the cost of tuition at a state university was $4,300. During the next 8 years, the tuition rose 4% each year. Assume this rate happens forever. So every single year, it's increasing 4%, then 4 more percent, 4 more percent, so on and so forth. Write a model that gives the tuition Y in dollars, T years after 1990. So I'm going to go through, I'm going to have the same equation, so if this helps you, you can write down the general equation. But I'm going to go through what they gave me and kind of pick apart some of the pieces. So looking at this, 4,300 is my initial value, right? Initial amount of money it costs to go to college. Then it says, well, it rose, so it's increasing. I should do this in a different color. It rose at a rate of 4%. Well, I'm going to take that 4% and I'm going to switch it back into a decimal, and I have 0.04. It wants to know modeling equation for t, okay, for years. So I don't know t. I know a, plug it in. I have a 1 plus. I know r, so I plug that in. I don't know t. That's what it's asking. I could plug in a time frame, get out my answer. Plug in a time, get out my answer. So there, again, is my model. Okay, let's do this quick one here. Your friend looks at this graph over on the side and says it's an exponential growth graph. Explain why your friend is wrong. How do you know it is not growth? Okay, well, there's two kind of things, or two ways you could look at this. Your friend is wrong because this graph is in the direction of a decay, right? It is actually going downward. Okay, if you can kind of look at my graph. So you could say something like the graph actually is decreasing. And decreasing goes with decay. So you could say something like that. Or you could say something like, just in a different way, growth graphs should increase, and this graph actually decreases. Kind of sort of the same explanation, just kind of written in a different way. Something like that, like this graph is actually going downward. If you're still stuck in that, a growth curve, if you forgot, looks something like this. That's a growth. This is completely opposite. If you were stuck, I went too fast, you couldn't, get it all down, pause the video, rewind the video, go back and rewatch the video so that you know how to do your homework.